Welcome to Optimation's educational video series on nesting technology. The purpose of this video series is to provide you with a fundamental understanding of how nesting technology applies to your company. Whether you are considering upgrading your nesting technology or you just want to keep current with the latest advancements, you'll find valuable information in this series. Cutting regular or irregular shaped parts from raw materials is a problem that has been a part of manufacturing since its beginning. The art of creating a plan for cutting multiple shapes from a larger raw material is called nesting. Often nesting is thought of as the best way to lay out parts so that the least amount of raw material is wasted. This is a very limited view of the problem. In today's modern manufacturing, there are many other important factors that must be considered while material waste is being minimized. These include machine efficiency, schedule demand, part and order flow, and of course, unplanned demand. All of these components have a cost impact and must be considered in order to find the optimal solution. While material efficiency is often the first benefit that comes to mind when nesting, any of these additional factors may interact with material efficiency. The Venn diagram shows two important facts. First, there are many factors that must be optimized to find the best possible solution. And second, there is a common solution set that allows all of the factors to be solved. Inside this common solution set is where the optimal solution will be found. Now, often material cost is the largest cost factor in producing a part. So first, we'll concentrate on how different nesting technologies address material efficiency. Nesting problems are very large mathematical problems. To get an idea of just how big these problems can get, we'll look at nesting just 35 parts limited to orientations of 0 and 90 degrees. There are 70 factorial ways to nest the 35 parts. Or, put another way, there are over 10 to the 100th power ways to nest just 35 parts limited to only 2 orientations. This number is so large, even the fastest computer would take several lifetimes to create all of the possible nests. Clearly, it is not possible to brute force the nesting problem. Since this problem is very old and predates computers, a solution method for part selection was developed that a person could use that would tend to get better solutions than just randomly cutting the parts. The method is still in use today and is defined as list-driven nesting. List-driven nesting is simple and is used in many computer programs to approximate a solution to the nesting problem. Now, list-driven nesting uses the following steps. A. Order the parts in a list. In most cases, the parts are ordered from largest to smallest because this generally favors material efficiency. B. Place the first part in the list on the raw material and rotate it so that the center of gravity of the part is closest to a datum point. Now, often this is the lower left corner of the raw material. C. Take the second part in the list and place it on the raw material. If it doesn't fit, go to the first part in the list that will fit on the remaining raw material. Rotate this part until the center of gravity is closest to the datum point. Repeat this process until the last part in the list has been considered or the raw material is full of parts. The result of the above process provides one possible solution out of the over 10 to the 100 power ways the parts could be nested. As computers have gotten faster, more possibilities can be considered, and the number of lists and how the list is ordered have allowed additional solutions to be evaluated. Some list-driven systems make several ordered lists that each create one possible nest and then selects the best one of the group. So, for example, the list can be sorted by largest length, or largest area, or largest perimeter, or any other metric. The common characteristic of list-driven nesting systems is that there is one or more lists that determine the order the parts will enter the nest. The greatest attribute of list-driven nesting is that it considers only a few possible solutions and therefore can run quickly. The major disadvantage of list-driven nesting is that it can only embed one cost component in its list of parts. So, as an example, the list can be ordered by part size or by schedule, but not by both. So when considering list-driven nesting, be sure to evaluate the impact it will have on other cost components that may be important to you. A second nesting solution, called cost-driven nesting, has the ability to consider multiple cost components simultaneously. Now, this makes the problem much more complex, but provides a means to solve real-world problems. To illustrate this, let's refer back to our diagram. Let's imagine that each point in this circle represents a different possible nest. Inside this circle, there are groups of nests that satisfy a manufacturing requirement. There are nests that meet the material efficiency requirement, nests that meet the production schedule as well as unplanned demand, nests that can maximize machine throughput, and nests that keep your order flow manageable. Where two or more of these circles overlap, multiple manufacturing requirements are being satisfied. Now notice that the feasible range of possible optimal solutions where all costs are optimized is in the area where all of the circles overlap. By considering all of these factors or costs, cost-driven nesting reduces the number of possible nests down to a manageable number. So each nest solution considered is evaluated by applying costs so that the lowest cost solution can be selected. Cost-driven nesting also uses the mathematical technique of fathoming. Fathoming has the ability to search only within the narrower feasible range of solutions, and within that range, look at only the best solutions. Using these methods eliminates trillions of bad solutions that do not need to be considered and greatly increases the speed to find the optimal solution. This technique further limits the number of nests that need to be considered to a much smaller number of possible solutions. Cost-driven nesting works in the following way. A cost model is developed that will allow costing of parts. B, all costs are considered by calculating a value for each part based upon how it is nested. C, as a nest is built, multiple costs are considered. D, fathoming uses the experience of the first nest to eliminate possible nests that cannot be better than the ones already built. This eliminates all of the poor performing nests without having to build them. By using fathoming, only a few best possible nests are built, and the one that contains the optimal solution is selected. The advantage of this solution is that it considers the real-world manufacturing problem. If your production environment has multiple critical factors to consider when selecting which parts to cut together and on what machine, then cost-driven nesting may hold many advantages for you. However, since this system relies on rapid input of several costing factors, cost-driven nesting is designed to be integrated into an existing manufacturing environment. Integration points such as CAD and a production schedule are common to most manufacturers. This type of automatic system is not recommended for companies that want to interactively produce nests. Regardless of what type of material you're cutting, selecting the correct parts to nest is critical to maintaining a high material efficiency. However, there are several other factors that are also critical to effective material usage. We'll be covering the next two factors, part placement and part quantity, in our next video. We'd like to thank you for taking the time to watch this video and hope that you will continue to watch the rest of our series. If you'd like more information about Optimation or any of its products, or if you just have questions about the material presented, feel free to contact us by either phone or email. Optimation provides professional products with full professional-grade service. Our technologies are found nowhere else. Whether you have just one machine or many, this technology will deliver world-class economic performance.